Hi Bobcats! The previous video talked about the concepts behind how you create hybrid orbitals. This video is going to look a little bit more closely at identifying the hybrid orbitals in a molecule. Our main objective is to identify the hybrid orbitals and also the types of bonding by looking at the Lewis dot structure for a molecule or possibly even a VSEPR structure. This table helps to show how we're going to connect the concept of these Lewis dot structures to valence bond theory. With the Lewis dot structure, if you're showing a single bond, that single bond is going to be a sigma bond, right? One bond, it's got to be a sigma bond. There will be no pi bonds. However, if you have a double bond, out of those two bonds that have been formed, one of those is going to be a sigma bond and the other one is going to be a pi bond. And notice that we have 1 sigma plus 1 pi is equal to 2 for our double bond. If we have a triple bond, once again, that first bond is going to be a sigma, but then the second and third bond will be pi bonds. And so we have 1 sigma plus 2 pi's to get all 3 bonds in our triple bonds. And hopefully you did stop and go over and look at section 11.3 for the animations to kind of illustrate how all of that works. When you're looking at questions about sigma and pi bonding on a quiz or a test, they'll kind of be phrased along the lines of, okay, given this Lewis dot structure, how many sigma bonds are in the molecule? How many pi bonds? What hybrid orbitals are involved for this particular atom? What are the bond angles? Okay, so remember a couple of things here. For the bond angles, you definitely have to think VSEPR, right? If you're looking at a Lewis structure, everything looks like it's either 90 or 180 degrees, and that's rarely the correct answer. Hybrid orbitals, we're looking a little bit at valence bond theory, but I think we can associate the hybrid orbitals with particular VSEPR structures. Linear VSEPR structure is going to be sp hybrid orbitals. Trigonal planar VSEPR structure is going to be sp2, and tetrahedral VSEPR structure is going to be sp3. In fact, when you get into organic chemistry, they're going to talk tetrahedral and sp3 interchangeably, trigonal planar and sp2 interchangeably, and linear and sp interchangeably. And as far as the sigma and pi bonds, the first bond that's formed between any two atoms is a sigma bond, and then if there are two bonds or even a third bond, that second bond or that third bond will be a pi bond. So let's take a look at these examples. All right, in this structure, how many sigmas and how many pi's? Well, each one of the atoms that have been joined together here has a sigma bond. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma bonds here. And then where we have the double bond, one of those bonds is also a pi bond. The second bond is a pi bond. So 9 sigma bonds and 1 pi bond in this molecule. For the hybrid orbitals, we've got a couple of different scenarios going on. If we're looking at the outside carbons, if we're looking at the one that's here or the one that's here, the ones that are bonded to 3 hydrogens, they have a total of 4 electron domains around them, which means that they have tetrahedral electron geometry, and tetrahedral electron geometry means sp3. So both of those guys are sp3. This middle carbon that's bonded to an oxygen, it has 3 domains. 2 of them are single bonds, one's a double bond. So with 3 domains, that's trigonal planar, and trigonal planar is going to be sp2. Notice that if you add up these exponents, you get the number of domains. So S has an exponent of 1, P has an exponent of 2, 1 plus 2 is 3. That's how many domains there are. For the sp3 hybridized one, those outside carbons each have 4 domains on them. So sp3, the exponent on S is 1, 1 plus 3 gives us 4. In terms of bond angles, the sp3 carbons have bond angles of 109.5 degrees, and the sp2 has a bond angle of 120 degrees. If we look at this molecule down below, which is acetylene, we have 3 sigma bonds, because each spot where there's any kind of a bond, we've got 1 sigma bond. So sigma, sigma, sigma. So that gives us 3 sigma. And then when we have the triple bond, the second bond and the third bond are both pi bonds. So there are 2 pi bonds associated right there. So 3 sigma bonds plus 2 pi bonds. For hybridization, the carbon atoms here have 2 electron domains, which means that they are linear. When they are linear, the hybridization is going to be sp, and being linear, their bond angle is going to be 180 degrees. Whoops, hit the wrong button. Let's see. I can make that go away. Good. And then last but not least, I believe this molecule is styrene. When we take a look here, what sort of hybrid orbitals and such are we looking at? Sigma bonds, pi bonds? Okay, so for all of the bonds, there's 1, 2, 3. What I'm doing right here is counting sigma bonds, by the way. So 3 so far, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 sigma bonds. Then any place there was a double bond, there's also 1 pi bond, because that double bond is a sigma plus a pi. So we also have a pi here, and a pi here, a pi here, and a pi here. So that's 4 pi's. 16 sigma bonds and 4 pi bonds. In terms of hybrid orbitals, if you pick any of the carbon atoms in this molecule, you're going to find that it has 3 domains. And any and every one has 3 domains. And with 3 domains, the geometry is going to be trigonal planar. So 3 domains means trigonal planar, and trigonal planar corresponds to sp2 hybridization and a bond angle of 120 degrees. I hope that I can kind of answer this issue about bond rotation, why ethane is free to rotate about the carbon-carbon bond, but ethylene is not. I searched for a little bit and didn't find a good video already in existence on this. There's probably a good one out there. I just didn't find it in the amount of time that I had available for searching. So ethane is this molecule on the left, and ethylene is the molecule on the right. When you see E and E, that indicates a double bond, versus A and E is going to indicate all single bonds. With ethane, the hybridization on the carbon atom is sp3. We get a sigma bond formed as that sp3 hybrid orbital on one carbon overlaps with the sp3 hybrid orbital on the adjacent carbon atom, and it's cylindrically symmetric. So because it's cylindrically symmetric, there are no major barriers to the these 3 hydrogens that are out here on the end in this carbon, the right-hand carbon. There are no barriers for that carbon-carbon bond rotating. So if you can think of that skewer going through the middle there, and then the carbon on the end with the 3 hydrogens is free to rotate at any angle around there. Now, when you take organic chemistry, there are more complicating factors. There are things like steric hindrance, and they're eclipsed, and staggered conformations and things like that. So there's more to the story, but the main take-home lesson is that a single bond is free to rotate. When there's a double bond, though, this bonding situation is a little bit different. I'm going to redraw this ethylene molecule edge on to try to show the Vesper structure a little bit more than just the Lewis structure. So when we form this ethylene molecule and we have sp2 hybridization here, that's going to be with a 120-degree bond angle, trigonal planar structure. The hydrogens are all going to be in the same plane, and I'm trying to indicate them as being in a plane that's perpendicular to the computer screen by using the wedges and the dotted lines. And because we have sp2 hybrid orbitals, there's a leftover unhybridized p orbital. And for some reason, they like showing this a lot in purple. So I'll just show these unhybridized p orbitals in purple as well. And so these unhybridized p orbitals are free to overlap side to side and create that second bond, that pi bond. But that only works if the carbons are oriented in such a way that those unhybridized p orbitals are parallel to one another. If we start rotating one of these guys around that carbon-carbon bond, the p orbitals will no longer line up, and that's essentially breaking the second bond. Well, it takes a lot of energy to break bonds, and you don't normally have that amount of energy available to break the bonds. I mean, there has to be something else going on, like you're heating it to a real high temperature, you're zapping it with the right frequency of light. So ethylene just floating around in the gas phase like it normally does is not going to be able to rotate around that where we have the double bond. And so just in general, you can get rotation about single bonds. So rotation can happen for single bonds, but there's no rotation about double or even triple bonds. And it really boils down to keep the single bond, or to keep the double bond and the triple bond intact. The orbitals, the p orbitals, have to overlap side to side, and so that restricts the molecule from rotating. So there are some limitations on this valence bond theory. Valence bond theory is not the greatest for explaining something like the trigonal bipyramidal or the octahedral geometries. We can invoke something that involves d orbitals, like a d-sp3 orbital for trigonal bipyramidal, or d2-sp3 for octahedral, but there are some problems with that approach. And basically we can fix those if we level up and go to something called molecular orbital theory, which will be the theme of the next video. In this video, we work some examples of how to identify the hybrid orbitals involved and the types of bonds, sigma versus pi, from looking at the Lewis dot structure for a molecule.